Okay, welcome back. Now we have seen how to generate residue curve maps in a rigorous thermodynamic way, how to generate approximate residue curve maps. Now what we'll try to do is to use these residue curve maps to look at how do you separate components which form azeotropes by using a third component. So uh, let's start looking at separations now. Uh, just a couple of uh, things about nomenclature. So you will see all these terms being used by different people. Uh, I'm going to explain these terms one by one. So first of all, the component, the extra component that we add to separate a binary mixture forming azeotrope is called as an entrainer. Right? So entrainer is the third component that we add. The two components that we want to separate, they form an azeotrope, therefore you can't separate them by normal distillation. So we use a third component, and that third component is called as an entrainer. That's why we looked at the ternary diagrams, because then the entrainer and the two original components can be represented using a ternary diagram. The word heavy entrainer, so heavy means in terms of distillation, heavy means having lesser volatility or higher boiling point. That's the meaning of the word heavy. It is coming from this crude oil kind of jargon. Light crude means having more of the more volatile components. Heavy crude means having more of the heavy high boiling or less boiling components, or which tend to give you more residue. That's the kind of notation, or that's the kind of nomenclature that is used. Heavy means the component that is added is having even less volatility. It is less volatile than the two components. That's why the word heavy is used. So instead of heavy, we would use, sometimes we would use the term as a light entrainer. Light entrainer would mean that the entrainer that we have added has a lower boiling point. So it is going to be more volatile, right? So that's something about light and heavy. Okay, extractive distillation. The word extractive that we are going to use is in association, or is in conjunction with the word entrainer. The entrainer that is used has a preferential liking for one of the component, and therefore because the entrainer is heavy, the entrainer is going to take one of the components to the bottom of the distillation column, as if we are doing extraction. We are extracting the component and taking it down to the bottom of the column. So that means the entrainer takes one of the component which it likes more in the sense which has more affinity towards one component, takes one of the components to the bottom of distillation column, and the other component will go to the top of the column. So for example, if we are talking about separation of A and B, these are the two components that they form azeotrope. We add a third component C. Now if the third component C has a boiling point lesser, it is less volatile, then we will call it as a heavy entrainer. Now this C may have a preferential liking for A and B, which means affinity in terms of molecular interactions. A and C would like each other, or B and C would like each other. So then the C tends to hold back the B. Say for example, C likes B more than A. So for example, it may form a hydrogen bond, or it may form some kind of van der Waal interaction between C and B. Maybe there is a electrostatic attraction between B and C. Then B is going to be held back because of the C, and A is going to become more volatile. So if you think about the liquid phase, I am going to have liquid phase A and B, and I have added the third component C. Now suppose B and C, or B preferentially likes C, then I'm going to have lesser B in the vapor phase. I'm going to have more of A in the vapor phase, as if I have increased the relative volatility between A and B by adding C. I have made B less volatile because it is held back, because if you look at the thermodynamics, it has a sort of a let's say negative activity coefficient less than, not negative, activity coefficient less than 1. That means it is preferentially going to remain in the liquid phase, and Therefore, A will get enriched into the vapor phase as if the relative volatility between A and B has been increased by keeping more of B in the liquid phase and then allowing A to go more in the vapor phase. Now, if I distill this, I will get A to the top of the column, B and C will go to the bottom of the distillation column, as if B is extracted from the mixture of A and B by the third component that we have added. That's why the word extractive distillation. The word homogeneous means A, B and C form a single liquid phase at all compositions. They do not form two phases. Like suppose water was added, sometimes water aqueous phase would become one phase, organic phase would become the other phase. They split into two phases. So that does not happen. That's the meaning of the word homogeneous. If it does not, if it forms two phases, we would call it as a heterogeneous extractive distillation. Okay, so every word that is written here has some meaning. So we are going to look at first category. So let's say category 1, how to separate the two components A and B by adding a third component. The third component is heavier, therefore it is an extractive distillation and it forms a homogeneous single phase. Let me give you an example. So for example, acetone and methanol. So acetone and methanol, they form an azeotrope. It's a minimum boiling azeotrope. You can separate that by adding water. So we had done the residue curve map for acetone methanol water system. Do you recall that? If not, go back to the previous lecture and recall. What I would like you to do is recall and draw that RCM again, approximate RCM if you like. Propose a process flow diagram for the distillation strategy, how you would distill out acetone and methanol using water as a entrainer by doing extractive distillation. I want you to indicate the feed, distillate and bottom composition on the residue curve map, and I would like you to calculate the composition and quantities of all streams on the process flow diagram per 100 kilomoles of the feed mixture. Okay, do this for yourself. You may go wrong, doesn't matter. You may get it right in the first shot, doesn't matter. Pause the video, do it for yourself. Okay, so first of all, I'm assuming that by now you have paused the video and done the calculations or done the flow sheet yourself, process flow diagram yourself. Now let us try to see. So first of all, what we are going to do is look at the methanol, acetone and water ternary diagram and the residue curve map. So this is our residue curve map for methanol, acetone and water. So you see the azeotrope, minimum boiling azeotrope, and you see the water. If we add water here, now this is the residue curve map. This is how we had got it, and you would have been able to get it again. If you recall, this is how we had got our residue curve map. Now let's start using it. Now what do I have? I have a feed which is 50 mole percent acetone. That means our feed is somewhere here. So this is 0.5. This is our feed. Now think about a strategy. If you add water, what will happen to the mixture? So what I have is equimolar mixture of acetone and methanol. Let's say in terms of mole fraction, 0.5 and 0.5 equimolar. Suppose I add water and I mix them together. Right? Now my mixture will contain acetone, methanol and water, isn't it? Suppose I add 1 mole. Now the mole fraction in this mixture of acetone, methanol, water, where would that be? That would lie along the line between water and this feed. So if I draw a straight line, it will lie somewhere along this straight line. If I add a large quantity of water, the mixture would have a mole fraction somewhere here. If I add 1 mole of water to 1 mole of the mixture, I would be at a midpoint between the two along this line. If I add too little water, I would be closer to the feed point. Right? So this is like too large water. Let's say this is like a midpoint. 1 mole, 1 mole. Maybe here too little water. Okay. Now, suppose let's say I add say 3 moles of water. So now my resulting mixture will have 4 moles. I would have 0.5 moles of acetone, 0.5 moles of methanol and 3 moles of water. So if I want to depict that, I would be say somewhere here, let's say here. I'm adding 4 moles. Out of the 4 moles, 3 moles are water. That means along this line, if I measure the length of this line, suppose this line is 12 centimeters, then I would be 1/4 way in this direction and 3/4 way from here. So this would be the split, 3/4 and 1/4. That's how this point will come. Recall this from your ternary diagram concepts from your undergraduate lecture. Now if I distill this mixture, so if I distill this mixture now, now what will I get? Look at the residue curve maps. Where is the residue curve map in this? At this point, residue curve maps are going to be like this. Something like this, isn't it? So if I distill this mixture in a continuous distillation column, let's say I have a very tall column, very large number of theoretical stages, very large reflux, I should be able to get pure acetone as a distillate. And the bottom of the column would be, remember, the feed, the distillate and the bottom, they lie on a straight line. We have seen that in a ternary diagram. The bottom product would be essentially a binary mixture of methanol and water. So if I distill, let's say we have large number of stages, large column, large reflux, I will get pure acetone at the top. And I will get a acetone and methanol mixture. Sorry, at the bottom I will have a methanol and water mixture. This I can distill. Now what will I get at the top? Look at the residue curve maps. Residue curves are pointing towards water. So bottom would be water, top would be pure methanol. Essentially, if I have a large column and large reflux, and this water now I can always recycle. Right? So I have separated. So if you look at this as a pure whole plant, water recycle is inside the plant. I have fed a mixture of acetone and methanol to the plant, used 2 distillation columns, I got pure acetone and pure methanol. Right? It turns out that I don't even have to do this mixing separately. If I do mixing separately, that's fine, but I don't have to do the mixing separately. I can even add the mixture, or I can even generate the mixture inside the distillation column itself. So I may have my feed here. I will add feed containing acetone and methanol. I will add water here. On this distillation column itself, that mixing will happen, and it is as if this water now is extracting the methanol and taking it down to the bottom of the distillation column and leaving pure acetone at the top. Of course, the reflux is there. All those things are there. I am just not shown the reflux. Right? We are assuming that the columns are fairly tall. Then only you will get pure acetone. Otherwise, you will get a mixture of acetone and water and little bit of methanol as well. But as if water has taken the methanol down towards the bottom of the column. So that's why we call it as an extractive distillation. Okay. Do you realize that? Now if I have to do composition, so suppose I take 1 mole of the feed, 0.5 0.5 moles here. I add 3 moles of water, so moles if I am writing, I will essentially get 0.5 moles of methanol here, 3 moles of water here. I will get 0.5 moles of methanol here, 3 moles of water here. I will get 0.5 moles of pure acetone here. So these are in terms of the moles, and then mole fractions you can calculate, and this is how we are going to depict them on the process flow on the ternary diagram. This is our feed to the distillation column, right? Our feed, as if it is a combination of these two feeds. So that is our feed to the first distillation column, F1, suppose F1. Distillate F1. Distillate, this is our distillate from the first distillation column. Let's call it as D1 if you like, distillate 1. This is the bottom product, B1, bottom of the distillation column, first distillation column. Okay. Now bottom of the distillation column is now the feed to the second distillation column. Is the feed to the second distillation column. Methanol, pure methanol is the top of the second distillation column. Pure water is the bottom of the second distillation column. You see, so I have two distillation columns. One distillation column is B1, F1 and D1. That is one distillation column. Second distillation column is now the B2, F2 and D2. That's the side of this triangle. That's our second distillation column. Now you see how our residue curve maps are helping us. Suppose we had added too little water. Suppose we had added too little water. Now our feed would not have been here. Suppose I had added too little water. Now suppose I had added only 0.2 moles or 0.3 moles here. The feed would have been the combined feed of mixing, after mixing water and acetone and methanol, would have been here, let's say. So that would have been, let's say, F1. Now if I had distilled that, I would have got the azeotrope at the top of the top of the distillation column, and bottom of the distillation column would have been this mixture of acetone, methanol and water. So you see, we would have not have got pure acetone. We will get pure acetone only if we add large quantity of water, so that the residue curves tell us that I can get pure distillate. See, that's how the residue curve maps are helping us. Okay, and of course now we can do the actual material balance. We can calculate the reboiler area, we can calculate the condenser area. This is what is happening. This is the feed. Okay, it's for a different, it may be for a different case. Don't worry about the flow rates. We add the feed here, we add the water here. At the top of the column there is a condenser reflux drum. Reflux is going back. I am essentially getting pure acetone at the top. Bottom of the distillation, I have got essentially pure methanol and water. And now you see, methanol and water is very large quantity, because we want the feed to end up somewhere here. We want the bottom to end up somewhere here. We want the feed to be here, so that I get essentially pure acetone at the top, and we'll get the mixture of methanol and water somewhere with this composition. You see, now I do distill in the second column. This is our B1, that's our feed to the second distillation column. Now if I distill that, I will get pure methanol essentially at the top and pure water at the bottom, which I can recycle back to the distillation column. So I don't have to do the mixing outside, I can do the mixing inside the distillation column itself. These tray calculations will come only when we do rigorous calculations. We are only generating an approximate process flow diagram. So whether water is to be added on the 25th tray or the 30th tray or the 15th tray, all those you will come to know only if you do the distillation, actual distillation design using a proper thermodynamic model like NRTL or UNIFAC. Okay, I want you to pause and think about what we have talked about and see that you can understand whatever has been talked about. Let's take one more case. Okay, extractive distillation of acetone and chloroform. Acetone boiling point 56.1, chloroform 61. They form a maximum boiling azeotrope 64. We add benzene, has a boiling point of 80. So benzene is heavier than the two components, therefore it is a heavy entrainer, and it is going to preferentially extract one of the components and take it to the bottom of the distillation column. So it is called as an extractive because it is heavy. It is as if extracting one of the components and taking it to the bottom of the distillation column. So heavy entrainer, so extractive distillation. Okay, I want you to draw a residue curve map, approximate at least, propose a process flow diagram, indicate the feed distillate bottom composition on the residue curve map, the triangular diagram, and calculate and compositions of all streams on the process flow diagram per 100 kilomoles of the mixture. Okay, pause the video, do it for yourself. Don't go forward unless you have attempted yourself. You may not get the answer, doesn't matter, but attempt is what is important. If you attempt, you will understand what is missing, then you can go back and improve your understanding, then only you go forward. Okay, so here is the ternary diagram: acetone, chloroform and benzene. This is the azeotrope, this is the feed, let's say around 50% or 45%, whatever it was. Let's say feed contains 55 mole percent acetone. So 55 mole percent acetone, 45 mole percent chloroform. Right. This is a distillation boundary. Remember our residue curve maps. This is a distillation boundary. Okay. Now this feed, if I add benzene to this feed, I would be somewhere along this red line. Don't worry about this point B2, I would be somewhere along this red line. If I add too little benzene, I would be here. If I add sufficiently large amount of benzene, maybe I would be here. So let's say we are somewhere here. Now if I do the distillation, look at the residue curve maps. Residue curves are starting like this, residue curves. Then I will get pure acetone at the top, and the bottom would be essentially a binary mixture. We would be along this distillation, we would end up on this distillation boundary. The distillation boundary is practically coinciding with this side of the triangle. So if I add, let's say, acetone and chloroform in terms of mole fractions, or in terms of moles, if I take 1 mole of the mixture, or if I take 100 moles of the mixture, that's what we want to do, 100 kilomoles of the mixture. Acetone is 55 kilomoles and chloroform is 45 kilomoles. Now I add benzene here. Suppose I add benzene 300 kilomoles. Then I would be at a point, the mixture, I would be at a point 1/4 from the line joining benzene and the feed, and 3/4 of the distance here. Ternary diagram. So I would have 400 kilomoles acetone, chloroform, acetone, chloroform and benzene, 55, 45, 300. Now if I distill this, I will get essentially, if I do distillation with a very large reflux, with a good amount of reflux, with large number of stages, I would essentially get pure acetone here. How many stages would be required? That can be calculated by rigorous plate by plate calculation. But right now we are not doing that. We are just saying we have large enough stages, we'll essentially get pure acetone at the top. We will get a benzene and chloroform mixture at the bottom of the column. So this is our feed to the first column, F1. That's our point F1. This is our distillate D1, and this is our bottom B1 from the first column. Now we use that as a feed to the second column. B1 is nothing but F2. I distill that. What will I get at the top? Look at the residue curves. They are pointing towards benzene. So residue pointing towards benzene, I will get pure benzene at the bottom. I will get pure chloroform at the top. And of course this benzene we can recycle back to the plant and mix it with the feed. Okay, again, like last time, we don't have to do the mixing separately. We can do the mixing in the column itself. right? Turns out that you don't have to do this pure benzene. You don't have to go all the way to the pure benzene. Maybe you can stop at this B2. Maybe little bit of chloroform remains. It doesn't matter, because now that mixture of chloroform and benzene itself you can recycle. So this can be pure benzene, or it can be uh, uh, mostly benzene, but a small quantity of chloroform is acceptable. So let's say B2 is this. I don't have to go to pure benzene, because now if I have to go to pure benzene, it will cost me more. It will be more in terms of trays. It will be more number of trays. In terms of reflux, I will require a large amount of reflux. This chloroform benzene mixture, essentially containing large amounts of benzene, itself can be recycled back to the process to be mixed with this feed. To be mixed with this feed. So our feed was acetone and chloroform for 55 and 45. We mix this whole thing, little bit of chloroform, even if it contains, it's okay. So what we are mixing is not pure benzene and F, we are mixing B2 and F. That's why we have joined a line between B2 and F. And depending on how much we are recycling, this is our feed to the first distillation column. This is our first distillation column. B1, F1 and D is our first distillation column. And second distillation column is distilling F2, which is same as B1, to get B2 at the bottom and chloroform at the top. Okay, you see how our residue curve maps are helping us. We are all the time remaining inside this distillation boundary. If I had added little amount of B2, suppose I had ended up with feed here, suppose this was F1, then I would have got essentially acetone at the pure acetone at the top, but we would have ended up at this as B1. So my acetone would have remained in the B1. By adding sufficiently large amounts of benzene, we are ensuring that the feed to the first column is here, so that I end up with B1, which is essentially devoid of any acetone. The distillation boundary is practically coinciding with the side of the triangle in this part. You see that? So how the residue curve map is helping us to decide how much of the quantity to add, and then to plan the distillation sequence. Okay, understand this for yourself. Do this for yourself. If you have doubt, go back and again refer to the lecture, and then only go forward. So this is the sequence. Acetone and chloroform, we make the benzene rich solvent, which is added as an entrainer. Go to the first column, acetone separated, benzene chloroform mixture separated in the second column, chloroform, and then this benzene rich solvent which we recycle. And if there is any loss because of vaporization, column condenser losses, we can make up some amount of benzene. Pause the video and do these examples for yourself. Pause the video. Don't go forward unless you have understood these two examples. They form the basis of what is going to come next. So pause the video, understand for yourself, and then only go forward. Okay, let's go forward. Okay, next we are going to look at homogeneous azeotropic distillation. Now the entrainer that we are adding, A and B, suppose these are our binary mixture which is forming an azeotrope. We are adding an entrainer. Entrainer is C. Now the entrainer is light. Light means it is more volatile, so it is going to come to the top of the distillation column, and then we call that as an azeotropic distillation. If the entrainer was heavy, we had called it as an extractive distillation. When the entrainer is light, we call it as an azeotropic distillation. And again, homogeneous, the word homogeneous means I'm going to have no second phase. I'm going to have all as a single liquid phase. Okay, let's take an example just to understand what all these terms mean. Okay, so let's say benzene and cyclohexane using acetone as an entrainer. Okay, benzene boiling point 80 degrees centigrade, cyclohexane 80.64. They are very close. They form an azeotrope, minimum boiling azeotrope at 77.4 degrees centigrade with 54.2 mole percent benzene. We use acetone as an entrainer. Now you look, acetone boiling point 56. It is lower than 80. So therefore it is a light entrainer. Light entrainer means it is going to come to the top of the column, and therefore we call it as an azeotropic distillation. So wherever there is a light entrainer, we will call it as an azeotropic distillation. Wherever there is a heavy entrainer, we will call it as an extractive distillation. Now, problem is acetone forms minimum boiling azeotrope with cyclohexane at 53.4 degrees with 74.6 mole percent acetone. That's one extra azeotrope that acetone is forming with one of the components. Okay, so assume that the binary feed contains 75 mole percent benzene and 25 mole percent cyclohexane. I would like you to draw a residue curve map and propose a process flow diagram, indicate the feed, distillate and bottom compositions on the residue curve map, and calculate compositions and quantities of all streams on the process flow diagram per 100 kilomoles of the feed mixture. Okay, pause the video, think about how you would like to do this. Pause the video, pause, do it for yourself, then only go forward. Attempt it yourself. Only if you have attempted yourself, then only you will understand how then only that will improve your thought process, that will help you to decipher how it is to be done. Okay, here is a possible solution. First of all, let us draw a approximate residue curve map: acetone, benzene and cyclohexane. So if you look at the binary side of benzene and cyclohexane, there is a minimum boiling azeotrope here. So the residue curves are all pointing towards the cyclohexane, away from the minimum boiling azeotrope. Okay, now acetone and cyclohexane again forms a minimum boiling azeotrope, that is here. So the residue curves are pointing away from the azeotrope. Binary side of acetone and benzene, residue curves will point away from the acetone towards the benzene. Okay, you will see that there is a one distillation boundary here, that is here. There is a distillation boundary here. It's a line joining two azeotropes and the residue curve. So point number one is, if you are not satisfied, if you are not comfortable, if you have not done it yourself, point number one, let me write it here. Point number one is generate approximate residue curve map for yourself and see that it is like this, that you get a distillation boundary. Now what is our feed? What is our feed? Feed contains 75 mole percent benzene and 25 mole percent cyclohexane. So feed is somewhere here. Well, 75, 25 may not be exact, but okay. Sorry. That's not the feed. Feed is here. This is our feed. Benzene is here, cyclohexane is here. So the feed is a 75 mole percent benzene, 25 mole percent 75 mole percent benzene, 25 mole percent cyclohexane. this kind of separation, benzene and cyclohexane, is a very common kind of separation in petrochemical complexes. You want to separate the aromatics from the naphthenics, which are not aromaticized, because the aromatics will go to different route. They will go towards making xylene, paraxylene, and so on, right? Whereas cyclohexane kind of compounds will go in the um, gasoline, and it will go towards aromatizing the process. That's why separating aromatics from non-aromatics is a very important step in petrochemicals and refineries. So it's a very important kind of separation that we are looking at. Okay, so this is our feed: 75% benzene, 25% cyclohexane. Now if I mix acetone with this, let's say I mix 50-50. This is my mixed feed. Now if I distill out, I would be able to get, what will I get if I distill this mixture? Look at the residue curves. Residue curves are pointing towards benzene. That means at the top we will be close to the azeotrope, maybe somewhere here. And the bottom we will get essentially pure benzene. So if I have, let's say, benzene and cyclohexane, let's say 1 kilomole of the mixture, I have, or 100 kilomoles of the mixture, I have 75 kilomoles of benzene, 25 kilomoles of cyclohexane. I mix acetone with it. Let's say I mix 100 kilomoles of acetone. My combined mixture would be somewhere here, midway between the line joining the feed and the acetone. Right? Do you agree with that? Now if I distill this, use a good amount of reflux, use large number of stages. How many stages, how much reflux will of course come from actual rigorous calculations, but essentially I will get pure benzene at the bottom, and I will get a binary mixture of acetone and cyclohexane here. Binary mixture. So benzene I would get 75 moles here, cyclohexane 25 moles here, and 100 kilomoles of acetone. We are ending up very close to the azeotropic mixture. So this is our T1, this is our B1. Now I have got acetone and cyclohexane mixture, but acetone cyclohexane also forms an azeotrope. So I can't separate acetone and cyclohexane, but I can use a property that acetone is highly soluble in water and cyclohexane is practically insoluble in water. I'm taking help of some other property. So if I send it to an extraction column, of course extraction is the next part of our course, I put water, I will get water acetone at the bottom extracted out, and I will get cyclohexane essentially pure. And then water acetone I can distill out, I will get acetone at the top, I will get water at the bottom, I will recycle this water. So if you look at the plant, the whole plant will consist of one distillation column, two distillation columns, and one liquid extraction column. I will get, if I feed this mixture, oh, my acetone also is going to be recycled. Acetone is also recycled. That's as an entrainer. This acetone I am recycling back to here. Okay, so if you look at the blue, that's the whole plant. Benzene cyclohexane is fed. I get cyclohexane out from the extraction column and benzene out from the bottom of first distillation column. So I have two distillation columns, one liquid extraction column. That's because acetone and cyclohexane form an azeotrope. If they had not formed an azeotrope, I could have done the distillation. I would have got acetone at the top of the distillation column, cyclohexane at the bottom of the distillation column. But they form an azeotrope, so it's not possible to separate them. So I make use of one more property, that acetone is highly soluble in water, cyclohexane is insoluble in water. So I do a liquid extraction. Okay. So the first column is our azeotropic distillation column. It is an azeotropic distillation column with acetone as an entrainer, light entrainer. It's called as an azeotropic distillation. You see that? Pause the video, understand for yourself. Okay, this is how it's going to look like. Feed. cyclohexane and benzene feed to the first distillation column. That's our azeotropic column, azeotropic distillation column. I get benzene at the bottom, cyclohexane, acetone azeotrope at the top, which I'm feeding. Acetone is fed as an entrainer, essentially cyclohexane acetone azeotrope. I do liquid extraction using water. Acetone and water mixture comes here. Cyclohexane is separated out. Acetone and water, I feed it to a distillation column. Water I get at the bottom, which is recycled to the extraction column. Acetone I get at the top, which is recycled to the azeotropic distillation column. Now you see how our residue curve map is helping. Suppose I had added too much acetone. Suppose I had added too much acetone. We would have been somewhere here. The mixture would have been somewhere here, which is the feed to the first distillation column. Now if I had done the distillation, I would still have got benzene at the bottom. I would have got this mixture at the top. If I had added too little acetone, my combined mixture of acetone, benzene and cyclohexane would have been here. If I had distilled that, I would have got benzene at the bottom, but I would have ended up on the distillation boundary as a mixture. My benzene would have been left inside the top of the distillation column. So if this was the feed to the first distillation column, D1 would have been on the distillation boundary, B1 would have been on the pure benzene would have come at the bottom, but top of the distillation column we would still have had benzene. I would have a ternary mixture of benzene, cyclohexane and acetone, which would have been complicated to do, to separate. Benzene would have remained. So you see how much acetone is to be added is, the ternary diagram, RC residue curve map, is helping us to decide how much acetone to add, so that after distillation I end up essentially, I don't end up near the boundary, I end up on a binary mixture of acetone and cyclohexane. So you see how our residue curve maps are helping us. You see that how residue curve maps are helping us. Pause and think about it yourself. Do these calculations, do these things yourself, and see that you have understood what you are talking about, what we are talking about. Pause the video, understand. I'm going to stop here. We are going to continue in the next video, but understand for yourself. Don't go forward to the next video unless you have understood all the concepts here. So let's stop this lecture here.